Welcome to the basics of integration. This first episode I'll be showing you about the power rule and notation and other rules that are used in or even how or what is integration or an integral. So we start here by looking at a derivative and an integral. An integral is almost like the reverse of a derivative. With the derivative, let's say you start here with a function and you derive it, you're finding the rate of change. Then you would come over here. And when you want to go back, usually to either find the function, or if you go back far enough, you can use it to find the area of functions and whatnot. But the notation you should be familiar with if you're doing this for a course or whatnot is generally a lowercase f will signify a function. F with a dash will signify a derivative, and F with two dashes will be the second derivative, and so on. But if you go back and you see a capital F, generally that means the integral. That's Lagrange's notation. Leibniz has his y's and dy over dx and whatnot, but I haven't really come across a letter he uses to describe an integral. It's usually you just start with the derivative and you go backwards to the y. You don't start with the y and go backwards. You start from the derivative and go backwards. Whereas with Lagrange, you can start with the function and go back to a bit of notation he uses for the integral. You can do it however you want, so long as whoever's marking or looking at it, if anyone else will, they know what they're looking at. You can assign other letters. If you want, you can assign W as your integral letter, but if the person who's looking at it doesn't know what it is, you've got a problem. So it's just safer if you're using this, capital. If you're using that, start with this and go back to that. And I also show you the operator. Essentially, when you're doing a derivative in Leibniz's notation, you have this here is the operator. That's a bad box, very bad. But that's the operator. So you've got the function and you're multiplying it to you got the derivative of whatever you're multiplying it with respect to the variable. And that's when you want to find the derivative of something, you use this operator and then put the function, and that's proper notation. But over here, this is what you do for the integral. That's what you do for the integral. You have this little line, not little line, but a very long line, not like really far over or really far back. Just try and have it straight or on a little bit of an angle to the right, and two little curves at the end. And that, along with the function in the middle and a dx on the end, signifies the integral. That's like your operator. So when you put your function inside this, that shows that you're finding the integral of the function that you put within these two outside parts. So it's funny, people use, when they do derivatives, a lot of people I've seen, their proper notation is Leibniz's way, whereas when they do integration, they like to use Lagrange's way of doing things, which is when you see the f prime of x and whatnot, instead of the y's and dy dx and whatnot. They like to use the dx over here, but when they resemble functions, they like to show them in Lagrange's way. Sometimes they'll mix them, but yeah, this is the most common way I've seen integration, where you have the operator for the integral. When the operator for when you're integrating something, you've got your function, and the result is the integral of that original function. I hope that makes sense. But nevertheless, here we have the power rule. Now, when we do the power rule with derivatives, you have x to the power of n, and when you derive it, you take the power down to the front, and then you take 1 off you take the power down and multiply it to x, and you take 1 off the power. That's the power rule. But in derivatives, with integration, you have this here. When you have x to the power of n, and you integrate it, you get x to the power of n plus 1 over n plus 1, and then that's all plussed against c. C is a constant, like a number, and I'll explain in a minute in the next couple of pages what this is, but that's the power rule. That there is power rule. Here is an example. You have x to the power of 2, and the integral of that is x to the power of 3 on 3 plus c. So yeah, you've got the 2, you've taken the 2 plus the 1, which makes x to the power of 3, and then you've put it over 2 plus 1, which is 3. And then you've added the c. I'll show you the reverse of this so you understand. See how you start with x squared and you end with x to the power of 3 on 3 plus c? Well, just like how c is a number, I've made it 5. I'm doing the derivative here. So I'm showing you that when you start with x to the power of 3 on 3 plus a number, and you derive it, you end up with x to the power of 2. Because the reason you add 1 to the power and then put that on top of the old power plus 1 is because when you derive it and you bring the 3 down, you'll be multiplying the 3 by x squared. So to get rid of that 3, you need to divide by 3. That's why there's this n plus 1 on the bottom. Because when you derive it and you bring the power down, you're going to need to get rid of that. Well, not get rid of it, but that's how it works, and that's the derivative. That's the reverse of the integral. That's trying to give you a brief understanding of why you divide by the old power. And here is some more rules that are generally used and integration. You have a constant rule where when you find the integral, when you're integrating a constant, or you're finding the integral of a constant, which I've labeled a, that can be 7, 10, 30, whatever, it becomes a multiplied by x plus c. The reason you write c, by the way, is because when you're integrating it, you don't know if there was a number there or not, because when you derive it, any constants you get rid of. So if you were, say, back over here, when you derive this, we get rid of the 5, because when you derive a constant, you get rid of it. So if we reverse this, and we didn't know that it was 5, we wouldn't know. So we just write c, because there could or couldn't be a number, but we don't know, so we write c. Anyway, so you have a, and when you integrate it, you get ax plus c, because if you were to derive ax, it would become a, because an x to the power of 1, when you derive it, you take 1 off the power, and it's x to the power of 0, which ends up being a times 1. So you add an x to it. If it was, so it's not, that's, I won't say what I was going to say. It might confuse you a bit more. Yeah, a bit more. But generally, if you have a number and you integrate it, you will have that number multiplied by x, and then you would add c on the end. Always add c. I know in my classes, when people don't add c, they actually get marks taken off, and it's just such a simple thing just to add the c on the end. And here, enough of that, here is the multiplication by a constant. So if you have, you've got the operator, you've got a constant multiplied by a function. You bring that constant out the front, and you can still do the integral of that and then multiply it back onto the constant. Just like here, you have the operator and you have 7x. You bring the 7x, you bring the 7 out the front, and then you integrate the x. It doesn't make a difference on a small scale example like this, but when you've got brackets and other things and powers and whatnot chucked in there, it can actually affect it when you get to your end result. So that's multiplication by a constant, and that's the constant rule. Here, as the last two things I'll talk about, which is the sum rule and the difference rule. Basically the same thing, very simple. You have your operator, again, and inside that you have a function fx, and you're adding it onto a function gx. It's not like derivatives. With derivatives, it does happen, but you don't think about it, or you don't do it that way, where you have x squared plus 3x. You usually just derive it, put a plus sign, and then derive the next one. Without writing any notation or anything. With this, it's like the same thing, because you have fx plus gx, so you derive the first part, and then you plus it onto the derivative of the second part. These are sort of things that you just end up doing without thinking about them, but that's how it works. And with a difference, you have a function take another function, and so you find the integral of the function, each function separately, and you just subtract one from the other afterwards. So that is my intro into integration basics, and I hope that helped. Thanks for watching.